My name is Eran Inbar and I'm the CEO of Prisma Photonics. And in the coming talk, we will present a world record in pipeline leakage detection based on fiber sensing. So I'll wait for the presentation to upload and we can kick off. Thank you very much. So before diving into the technical details, a brief about Prisma Photonics. The company was founded 3 years ago, and our sole and exclusive focus is smart physical infrastructure based on next generation fiber sensing. And when we're saying next generation, we're referring to our proprietary hyperscan technology. And in this presentation, we will demonstrate the capability or the advantages that using this architecture can bring into smart physical infrastructure and mainly to pipeline monitoring. So oil and gas pipeline monitoring is definitely one of the main area of focus for us, but we're also dealing with other physical infrastructure monitoring, for example, electrical grid monitoring, perimeter control, railways monitoring, subsea infrastructure, smart roads, and also physical cybersecurity of optical network. I would start with a brief about the concept of fiber sensing, and then we will dive into the detail. The idea in general is instead of spreading multi-thousands of sensors along the pipeline, we will use an optical communication fiber. It's a standard optical communication fiber, and in many cases, it's a pre-existing fiber. The meaning is that if there is a optical communication fiber close to the pipeline, we can use the fiber and then we don't need to install anything. And that's why we call this technology a sensor-free. No need to install basically any sensor. So what we're getting overall is a very clean and elegant architecture. We have the pipeline, we have the fiber, and then once every 100 kilometers, we have a system. It's called optical interrogator. The system is placed in the customer communication room, so no need for any new and dedicated location. And any system can turn 100 kilometers of fiber into sensor, and this distance, 100 kilometers, is also a world record for fiber sensing monitoring. So we have those interrogators spreading over 100 kilometers, and all the information is presented in a single and consolidated user interface that it's usually located in the customer command and control room. The question would be, what can be detected using this technology? So here are the main use cases, and we will start, of course, with the first and foremost, leakage detection. So using fiber sensing, we can detect very small leakages. Later on in the presentation, we'll show actual results. How small can it be? And it's not only detection, but it's also localization. So we can detect the event and get the exact location in a resolution of few meters. So basically, we can pinpoint exactly where each one of the events is happening along the pipeline. Additional, for example, operational aspect that can be monitored is inline pigging devices and variety of critical infrastructure protection topics like theft, vandalism, third-party interference, of course, mechanical and manual digging close to the pipeline, and activities like pedestrian and vehicle movement. I said detection and to detect, but basically, the main challenge is not to detect, it's basically to classify. What we would like to say that along a pipeline in a real life scenario, there could be many thousands of events. It can be close to a highway, there could be construction site, there could be farmer walking nearby. So we're having many thousands of events, most of them are not relevant. So a challenge is not only to detect them, this is relatively easy. The main challenge is to classify them and to present to the user only the relevant event, only the one that risking the pipeline or are interesting to the user. If not, there would be a lot of irrelevant information, and it mainly cause a very high false alarm or nuisance alarm rate. Let's go into example to explain the aspect of classification. So what you're seeing here is a technical user interface. So a part of the map that we would see the event on it, there is also the technical part, the blue rectangular in the upper part of the screen, which is called a waterfall. And the waterfall is a presentation of a map when the x-axis is the location along the pipeline and the y-axis is the time. So we can see where the event is happening and where it is evolving. On the left side of the screen, you see what's happening. We have a digger close to the pipeline, but the engine is off, the digger is not working, we're not seeing it. But what we can see, for example, is a very strong signal of a water pump. You can see yellow marking with the icon of the pipeline. Let's see what's happening on the right side once the digger turned the engine on. Once it's turned the engine on, we can immediately detect the digger and we know that there is something. But if we will give an alert right now, there would be probably a lot of false alarm because there is a lot of other events with similar signature. So right now we know that the engine is on. Next step, the digger is start digging. After the first ground hit, the first digging activity, we turn it in what we call a yellow event. It's not yet an alert, but we start to build the story. We see engine, we see first digging, and after the second digging, we have a high level of confidence to say, okay, this is an alert, and we can classify it. We can say that it's a digger. We know the exact location, and we can assure that because we classified it properly, that the false alarm rate or the nuisance alarm rate are very, very low. So let's go into the main course of this talk, and this is the leakage detection, and thank you for your patience waiting for it. But before starting to present leakage detection results, let's speak about how we're testing this event. Because I guess that anybody can guess that to generate a leakage from a high pressure gas line or an oil pipeline, this is something, of course, which is completely not practical. So we need to build some kind of a simulation field test to do it. And it's quite a complicated simulation field test, and we will show you why. And that's why you would see very, very few publications about testing that been done in those environments. And furthermore, you would see that there is a lot of variance in building this field test. For example, what is the distance between the pipeline to the fiber? What is the size of the pipeline? What is the pressure in the pipeline? What is the pressure of the hole? What is the type of fiber cable are we using? Is it in conduit or not? What is the orientation of the leakage toward the pipeline? So there are a lot of scenarios, and believe us, based on our experiment, each one of them has its own unique signature. So if I would build just a single case and test it, in real life scenario, maybe I will have a different case that I will not be able to detect it at all. So this is a big risk. And that's bring us into the complexity of building our field test. So what you can hear, and this is an actual picture of the field test, we have multiple type of pipelines, different diameters, different pressure. We have a lot of fiber in different location, different configuration, part of them in conduit, part of them not. We have a lot of oil with electric valve that enable us to generate different kind of leakages. Eventually, this field test that was, of course, after it buried in the ground, can generate a lot of scenarios. We can test the system in those scenarios and assure the robustness of the solution. So this is a 3D illustration of the field test and another one. And now we're ready to go into the leak detection results. And let's spend a minute to explain how we will present the results. So on the left side of the picture, what you're seeing is the waterfall, the same map, that seismic map that we used in previous slides. Just to remind, the x-axis is the location along the fiber, the y is the time. And you can see a black dashed line that mark an actual leakage. So you can see that the leakage, seen in yellow, it's very distinguished, very easy to detect. But as we mentioned previously, the challenge is classification. You can see that right to it and left to it, we have also other strong signal from background activities. So it's not only how to detect it, but how to classify it, how to eliminate all those background signal. And what we are doing, if I would like to use a very simplified explanation, we're using something which is close to what, for example, the application Shazam is doing when it's trying to know what song it is based on the music. We're trying to look at the signature of this signal. We're looking at what it's called a spectrogram, which is the frequency content of the event. And here in this spectrogram, the x-axis is the frequency of the signal and y is the time, so we can see where the leak starts, where it ends, but more important, we see the frequency content and we can analyze it and classify it with a very high confidence and very low false alarm rate. So once understanding it, let's go to the results. And first, let's speak about gas pipeline leakage detection. And what is today the industry standard? If we're speaking, for example, on SCADA-based or flow measurement systems, usually we're speaking about something like a leakage of 1%. What is 1%? The meaning is that when I have a leakage which is equivalent or higher than 1% from the flow in the pipeline, I can detect it with high confidence. State-of-the-art fiber sensing today can offer 10 times better. So we're speaking about 0.1%. Take a look at the picture here, and let's start with the lower right side. We're seeing a leakage of around 1,000 standard liter per minute, which is equivalent to something like 0.01%, 10 times better than the industry standard. We're seeing a very clear signature of the leakage that allows us a very high confidence decision when detecting this leakage. Let's move forward to the left lower side. We're seeing a smaller leakage, 650 standard liter per minute, which equivalent to 0.006, still a very definitive leakage signature. And on the upper right side, this is a very low leakage. We're speaking about 200 standard liter per minute, equivalent to 0.002%, which is roughly 50 times better than the industry standard. And of course, it's no need to explain what can be the benefit between detecting leakage in a very early stage, a very low leakage, rather than detecting it when it's quite significant, and we're speaking about thousands of liters per minute. We can look at how detection over time is look like, and let's look at the upper middle picture. What we see here is the spectrogram of a 650 standard liter per minute leakage. And below it, on the middle lower picture, we can see how the logic of the detector input, it's look over time. So we see when the leakage start to evolve, we can see that the signal is crossing significantly the threshold of detection. So we have a very high confident detection over time. Let's look about liquid leakage detection. And here we can see the signature of a liquid detection leakage of 20 liters per minute, equivalent to 0.02. Once again, the signature is very clear. We can see in very high resolution the frequency content of the signal that allow us to achieve high confidence in the detection and reduce dramatically the potential false alarm rate. Another thing that I would like to mention, I think it's very important, is that those detections methods are not using any kind of transient or momentary effect. There is a trend speaking about transient effect in the leakage. In the minute that or the second the leakages happen, there is a transient effect. There is a shock wave propagating in the pipeline, and if you're trying to detect it, it's something that if you missed it, you will not detect it anymore. So this is a high risk singular event that you are trying to catch. And furthermore, if you have a leakage that evolving over time, starting with a small hole and evolving slowly, one can claim that you will not see any transient effect during this progression of the leakage. So I would say that there is a risk relying in your algorithm on those transient effects. And this method, even though we presented leakage which is 50 times smaller than industry best-in-class results, is still not relying on any transient effect. So this is something that we can detect all over the leakage for seconds, minutes, and even hours ongoing. So just to summarize what we present here in this talk, it's the world record in fiber sensing pipeline leakage detection based on our proprietary HyperScan fiber sensing technology. We demonstrate gas leaks that going below 200 standard liter per minute, which equivalent to 0.002%. Another important aspect is the robustness of this method. So we are not relying on any transient effect, and this method is not relying also on the architecture of the installation of fiber versus pipeline. So we tested it in different pipeline diameter, different pipeline leakages, different fiber position, different fiber types, and different type of fiber installation types. So I would like to thank you for your attention, and we will be glad to try to answer any question there is. Thank you very much.
Thank you, Eran. And thanks for this good information. I have some questions on my own. You showed the test bed that you had made. There, all the pipelines, if I remember correctly, were plastic. So they weren't. Okay.
No, they were metal. Okay. What you see in this picture is plastic was part of the conduit that we put. So we tried fiber in direct, buried in the ground, and fiber in conduit. So you have the pipeline, metal pipeline, and then you have multiple fiber in different orientation and also different kind of installation.
Okay. And then about also when you detect the location of the leakage, what's your precision? How many plus minus meters can you be in the range with?
Okay. So I think that one of the benefits of the fiber sensing concept is the resolution. So we can reach resolution which is lower than 10 meters. So it's plus minus few meters over 100 kilometers of detection. So basically you can bring the user, if there is a need to dig, for example, to a very precise location, no need to guessing, you would be, you know, in resolution of few meters from the leakage.
Okay, I do see that there is a question in the audience also about your coming R&D. If you are the best already, where is there to go? Are you going to be even more precise and detect every molecule?
So this is an interesting question. So I think that the challenge, we have few challenges ahead. I would give you an example. We demonstrated in previous talk that when we install a system over real life pipeline, we measure for 50 kilometers over 24 hours more than 90,000 events. So classification is a real aspect. You need to classify tens of thousands of events per day. So one of our goals is to increase the classification capability. We believe that today, one of the advantage that you can bring to the user is eliminate the false alarm rate into practically zero, that the user will know that when you're giving an indication for digging or for pipeline, this is something with extremely high confidence, and this is something we're dealing with. We are doing more tests, collecting more signature, improving our machine learning algorithms, and the goal is to get better and better, because eventually there is a cost for sending the user to the field for something that potentially can be a false alarm.